Greetings. Now we will explore about complex numbers in general. So complex numbers are special numbers in the format of z equals to a plus bi, where I is a cert negative 1. Now the cert negative 1 is special because this value is undefined. However, it exists as an intermediate step to many calculations. Thus, this number was invented. Now, a thing to note is that when you square root a real number, eventually you get plus minus of a real number. But it only works when the real number is more than 0, as negative numbers, when you square root them, is ambiguous. When we explore about complex numbers, we usually split them into two parts. The first one being real part, which is RE, and imaginary part, which is IM. And if you take a look at imaginary numbers, powers of I at the diagram below, you can see that the pattern repeats every fourth power. And a thing to realize is that if you take I raised to the power of negative 1, you get negative I, and this pattern will still repeat. Now let's look into operations of complex numbers. So operation of complex numbers is just like just doing algebra, like add, subtract, multiply, divide. However, here's the thing about complex numbers. The utmost priority is to make sure the number format is in A plus BI, just to make sure. And you can use different methods. And in the case of division, notice that the complex number is at the top and bottom. To turn it into a format of A plus BI, you need to multiply it with the conjugate of the divisor for when you're doing division. And just a reminder, make sure you use all the powers of I that was explained in the previous section, so to make it into the complex number format. Make sure to do that when you conduct operations of complex number. Now let's look into the properties of complex number. So complex numbers can be represented as vectors in the Argand diagram, and you can see that when you represent them in the Argand diagram, you can find the modulus and the argument. So modulus is the magnitude of the complex number, whereas argument is the angle from the real axis. So you can arrange it with the trigonometric functions. Now argument of complex number must be between negative pi and pi, so to ensure that each and every complex number is unique, and make sure it matches to one of those in the trigonometric functions for each quadrant. Now the complex number has an exponential form and log form. For exponential form, you need to use Maclaurin series for e to the x, sine x, cos x, and include the imaginary number. Thus you get the exponential form of complex number as shown in the diagram. For the log form, just directly use the exponential form, although this is not so used often. Now when it comes to solving polynomials, you encounter something called conjugate root theorem. Means that when you decompose a function and even reduce the irreducible function, you actually get a pair of complex roots, and they must come in pairs, as neither of them are separate. Now square root of the complex function, you just do the reverse formation, make it square, and then you eventually solve it using the steps given. Now let's explore the geometrical effects when it involves complex numbers. For conjugation, you just change the sign of an imaginary number. Eventually what happens is that the complex number will be reflected on the real axis graph. The moduli of both complex numbers will be the same, except the argument will be inverse, to put it negative. For addition and subtraction, just use the vector addition from the vectors topic. For multiplication and division, the geometrical effect is different. For when you take the product of two complex numbers, you get the product of two moduli. Whereas for division, the quotient of two complex numbers will give the quotient of two moduli. For arguments, when you multiply, the arguments will add up to become the product argument. Whereas for division, you take two arguments and subtract together, you get the quotient argument. And another specialty is that when z is raised to the power of n, the modulus will give the exact same answer. And if z is raised to the power of n with argument, then you just take n times argument z. Now we explore is to see what happens when a complex number is multiplied by I. So it's very interesting if you look at this diagram. So when I acts as a constant, every I multiplication will cause the complex number to rotate by 90 degrees. Multiply by I a few more times and you see that it returns to the original function. And at every I you take, you raise the power of 4, it returns to the original function. Eventually, a circular path is formed. So multiplication I in the Argand diagram will result in a circle. Now, let's explore about locus, and there are three things I will discuss. So for the first one, this first part, z minus z1 equals the r with the modulus that encases the complex number. It will give you a circle with the center and a defined radius. Just make sure that the radius is a positive number. The second one, however, which is the involving two complex numbers with moduli on both sides of the equation, you will get a perpendicular bisector of the line that passes through the line of 2 points. So you can see that this is a perpendicular bisector, and the line drawn is equidistant from both points. For the third one, however, the argument of z minus z1 will result in alpha. So when you convert to the complex numbers of a plus bi, you get AB as a fixed point, and it represents a half segment drawn from AB and angle alpha from the positive real axis. So the locus pathways can be drawn on Argand diagram and it's used to obtain the area for inequalities. Now, before I end this video, I want to make a general conclusion. So here are some facts. Some of the videos that they see in my channel, they are somewhat incomplete. For me, I intentionally put them so that all of you are active and find your own proof, and also because some of them, like coordinate geometry, I need a proper tuition center to teach. That's why the topics feel incomplete or they seem out of place to you. And second, a lot of those A maths topics are intricately linked, such as those from secondary school to college level maths. You see a lot of them, and this is one of the reasons why I made all these videos so far. And the third, the handwritten materials that I made, they're mainly for guidance only. As for me, I think it's easier to teach with handwriting and explain why it's there in the first place. And you don't directly copy what was written there. You use it as a guide. And all of those videos I made are simplified for fundamental understanding. Some methods that I showed, such as the implicit differentiation, it is made as some students make a lot of careless mistakes there. And I would like to conclude the entire series. This is the Theoretical Pure Math series, and I hope all of you enjoy this video. Thank you.